Hello, everyone. My name is Maury Marquitz, and I am the president of the Fuel Cell and Hydrogen Energy Association. It is my pleasure to welcome you to the virtual national launch of the Roadmap to a U.S. Hydrogen Economy and introduce the Master of Ceremonies for this event, Dr. Jack Brouwer, who is Professor of Mechanical and Aerospace Engineering and Director of the National Fuel Cell Research Center and Advanced Power and Energy Program at the University of California, Irvine. Jack, it's all yours.
Thank you, Maury. Before we begin, I would like to review a few housekeeping items. I will begin this event with a review of the major findings of the roadmap to a U.S. hydrogen economy. This is a report developed by McKinsey & Company. We will then hold an initial Q&A session with myself and all the industry panelists. Following the Q&A, we will have a series of industry presentations expanding on the role of private industry in achieving the goals of the roadmap. And we will conclude with another Q&A session with the panelists at that time. Should you have any questions throughout the event, please submit them through the questions box in GoToWebinar. With that, it's my pleasure to begin. So U.S. companies from across many sectors of the economy have come together to develop this roadmap, and many of these companies are household names that you know and recognize. And they did this because they realized the benefits of hydrogen. Hydrogen offers opportunities for economic growth and employment, for introducing resiliency and reliability in our increasingly renewable electric grids and gas grids. It offers reduction in local air pollutants and reduction in greenhouse gases throughout all sectors of the economy. And slide advance is not going as quickly as I'd like. And the roadmap has been set up to lay out a 10-year plan with 4 phases: immediate next steps, early scale-up, diversification, and broad rollout. You'll see these phases identified in various aspects of the roadmap and in this presentation. And hydrogen offers unique characteristics as a zero emissions vector that enable it to be used broadly in many applications where other technologies could not offer a zero emissions option. And in this diagram, you can see uses of hydrogen throughout society, and only 5 of them will I identify here. Hydrogen offers the opportunity for power generation and grid balancing. It can do this in both centralized and distributed fashion, and it offers the opportunity for long duration storage that other options cannot provide. It can also be used as a transportation fuel, including materials handling applications, light and heavy duty applications, in fleets and rail applications. It can be used as a fuel for residential and commercial buildings, including blending it into the natural gas system and uses for combined heat and power. It is a required feedstock for many industries already, like ammonia, methanol, and refineries, and can be used in heavy industry like steel and cement manufacturing, and also as a feedstock for making aviation fuels and marine fuels. Finally, some industries need a reducing gas, and hydrogen can offer that reducing gas. Now, hydrogen is already widely used in society. We already have more than 11 million metric tons per year. It's about a $17.6 billion total market. It's mostly made by steam methane reforming of hydrogen to form the hydrogen, and some of it is made 23% as a byproduct from hydrogen refining. What you can see in the left-hand side is that current consumption is primarily in refining, 57% here, and in making ammonia, okay, very important chemical and fertilizer for our society. Other applications include metals, as you can see today. And all of the entities that have supported this supported this roadmap development, understand that we are transitioning from making hydrogen from natural gas by steam methane reforming to all low carbon means of making hydrogen. This is inevitable because we must do this for both greenhouse gas emissions reductions and criteria pollutant emissions reductions, and because jurisdictions have already made this the law throughout the world. In any case, you can make low carbon hydrogen in many different ways. Water electrolysis using low carbon electricity like nuclear, solar, or wind, or by using reformer-based hydrogen, the same way that we currently make it today from natural gas, but using carbon capture and storage, or a renewable gas feedstock, okay? We also have direct gasification of waste streams that we must manage in society forever anyway. A very good way to manage them is to make low carbon hydrogen from them, or as a byproduct recovered from other industrial processes. And the study here has been agnostic with regard to the pathways. All of these pathways are sustainable pathways that are supported by this roadmap. And as you can see in this one pathway of carbon capture and storage, there already are many formations for storing the carbon throughout the United States. And interestingly, they already exist where we are using hydrogen to make ammonia, for example, or to make hydrogen for other applications. So already we see a broad cross-section of the United States that's amenable for this very low carbon means of making hydrogen, as well as many other low carbon means of making hydrogen. And if we follow this roadmap, we will have roughly 14% of total US energy demand that will be met through this low carbon hydrogen. And what you can see is that there are today about 11 million metric tons, right, that are being used in society. And in 2030, you can see that it will grow to 14 and maybe 17 with some ambitious goals. And then by 2050, you can see that it's built up quite substantially by adding it as a transportation fuel, for example, here, or as a fuel for industry, or as some new feedstocks, for example, for synthetic jet fuel or as ammonia fuel for shipping. All of these could lead to a very large contribution that hydrogen will make to our energy conversion economy. And the roadmap identifies the pathways by which these hydrogen contributions to a zero emissions economy will be achieved. And many applications are already using hydrogen for these applications. So distributed power, fuel cells are currently an existing market. And the existing markets are shown in the dark blue, and the future markets from this roadmap are shown in the light blue. So you can see forklifts and material handling, already a very common use of hydrogen today, but it will grow substantially as we expect in the future. Trucks, vans, and medium and heavy duty trucks. There's a very small amount that are being used today, but growth is expected to be quite large in this particular market. And then you have light duty passenger vehicles also being used in California and around the world. And then we have the existing feedstock for things like ammonia production, and that's expected to grow a bit too. And then we have decarbonization short-term moves, okay? These are not necessarily underway today yet, but they are expected then to have some pretty substantial market in 2030 and a larger market in 2050. These include using it in steel, aviation, and industrial heat, also residential and commercial buildings. And then finally, the long-term moves are associated with low and medium grade heat in industry and even centralized power generation. And the roadmap has details of how these steps lead to these increases in market. And some of the immediate next steps are to build upon existing markets like the materials handling market and the distributed power market, but to expand them into some alternative new applications like data centers. And then in the early scale up, we see that we can use more and more fueling stations and vehicles, but vehicles of other types too, like the heavy duty and the medium duty and bus fleets and things like that. These are under development already today, as you can see from this figure. And then we diversify into other things like blending hydrogen into the gas grid. There's already pilots and engineering analyses that are underway around the world and here in the US for doing these kinds of things. And then finally, in 2031 and beyond, we have a broad rollout to all of these other applications like aviation and shipping, steel, and even this low and medium duty industrial heat. And we already have research and development and pilots underway in many of these applications today. And the participating companies have set an ambitious goal for meeting these roadmap milestones. And there are details as to each of these milestones and how they are being met in each of the sectors that are in the roadmap. So for example, if you look at fuel cell electric vehicle sales, okay, you can see that we're selling about 2,500 today per year. And that's what in the immediate next steps, we're going to try to sell more of them. By 2022, there will be 30,000 vehicles per year. 2025, 150,000, 1.2 million by 2030. Similarly, to meet that growing demand for hydrogen for these light-duty vehicles, we expect fueling stations to grow from the current number of less than 100 up to 4,300 for the broad rollout in 2030. Details of this are in the roadmap that you can find online. And this will lead to economic opportunities that are quite tremendous. Annual investment will grow from $1 billion in 2022 to $8 billion in 2030. And new jobs, great green jobs, will grow from 50,000 in 2022 to over 500,000 in 2030 during the broad rollout period. And hydrogen use throughout society will provide many benefits, economic growth, jobs, and use of domestic energy resources, a very important aspect in energy security and in renewable and sustainable energy. So you can see more than $750 billion in revenue, 3.4 million jobs by 2050, and all highly competitive source of domestically produced low emissions energy, and significant environmental benefits, a 16% reduction in CO2 emissions just from the use of hydrogen in society, a 36% reduction in nitrogen oxide emissions. These are really tremendous contributions that hydrogen can make to our sustainable economy. But we must be vigilant and act if we're going to make this roadmap a reality. To do that, we are setting the North Star first. In other words, setting dependable, technology-neutral decarbonization goals. Secondly, we have key actions that are required to create public incentives to bridge the barriers, to support infrastructure development like the hydrogen fueling stations, to include hydrogen-based options in government procurement, and to expand hydrogen use across many sectors. And then we need to support research and development for these longer term applications that aren't yet in use. We need to harmonize codes and standards for safety, and we need to support outreach and workforce development, and continue to be vigilant with regard to regulations as they affect the hydrogen economy. So for those of you who haven't yet seen this or downloaded your copy, you can get a copy of this at ushydrogenstudy.org. I encourage you all to download this roadmap for yourselves. And if you have any questions, please remember that you can submit them through the GoToWebinar Questions tab. Connor Dolan from the Fuel Cell and Hydrogen Energy Association will be facilitating the question and answer session and will be sharing questions from the participants. So, Connor, do you have any questions to kick things off?
Yes, one question to get things started is we hear a lot about electrolysis. What is the status of the green hydrogen market in the United States?
Well, green hydrogen is already being made from biogas that is being reformed to make zero emissions hydrogen. That's the main method that we are using today to make green hydrogen. But hydrogen, when it becomes ubiquitous, when we start to use it in all these applications that the roadmap identifies, will also need to be made by electrolysis using zero emissions electricity. And this is a market that's growing quite substantially, and I think will become competitive very soon. Dave Edwards from Air Liquide, would you like to mention something on this topic?
Yeah, I certainly can. So as Jack points out, there's a lot of methods to produce hydrogen. Electrolysis gets a lot of attention because it ties hydrogen to the electric grid. And if you think about additional solar and additional wind on the electric grid and the potential for curtailed power, hydrogen provides an excellent outlet for that energy. And electrolysis is the method that would be used for that. And much like other industries, the growth in electrolysis at these early stages brings down the cost of the equipment and hence brings down the cost of the hydrogen, making it competitive with other mechanisms for producing renewable and low carbon hydrogen. And some of our other panelists are certainly vested into the electrolysis process. And I think I'll hand it over to Andy because I know they've made some recent announcements in the electrolysis business.
Sure. Well, thank you, Dave. I would just like to highlight we recently purchased an electrolysis company, Jack, and the company was Giner EOX, and they've been developing electrolyzers since 1974. They've flown in space with NASA, and we bought them because we recognize that as renewable costs come down below 4 cents a kilowatt hour, hydrogen from renewable, green hydrogen, is cost competitive with fossil fuel-based hydrogen. And there's many places in the United States where wind power, especially during times of curtailment, solar power is available at those types of costs. And I think the market for green hydrogen will accelerate much more rapidly than many people may think because of the incredible reduction in the cost of renewables.
Thank you both for that. Other questions, Connor?
Great. Another question is, reductions in greenhouse gas emissions and pollutant emissions, is this just point of use or has the whole life cycle been considered?
The whole life cycle is considered, and this is very important. We must consider the hydrogen production technology, and there are many, many zero emission options. We highlighted them in one slide of the presentation. And then the end use. The end use as a fuel cell also produces zero carbon and zero criteria pollutant emissions. So you consider both the production and the transport and distribution and the end use to get these emissions reductions.
Great. Another question is, who will be contributing to making the 30,000 FCVs in the United States?
Let me ask Bob Wimmer to answer that from Toyota.
I think that's going to be a variety of different companies. Of course, Toyota has a wide range of vehicles I'll be speaking about later today, but there's other companies that have announced plans both in the US as well as globally to introduce the technologies both for light duty vehicles as well as heavy duty vehicles. So it's really going to be the entire automotive and heavy duty industry that'll be working to contribute to that number going forward.
Okay. Another question is, are there any specific federal policy measures outlined in this report as ways to support this ambition? Supply support, demand, market creation, regulation, or funding? I guess, Jack, would you like to start with that or kick it off to anybody?
I think there are a number of recommendations for both policies and incentives that would support the initial markets, because every time you introduce a new technology, you need some incentives, and then also to support regulatory environments that support hydrogen. So an example of this exists in California, where there are very strict pollutant emission regulations in various jurisdictions that put pressure on the incumbent combustion technologies that produce criteria pollutant emissions, at the same time that there are incentives for installing the zero emissions options. And so this is kind of the technique that works the best. And it works the best in Europe and in California and all around the world, where you have both a carrot and a stick. You have incentives for adopting the clean technology, and you have regulations for those that are harming our environment. Anyone else in the panel want to talk about that? Yes, Dave.
So I can bridge that a little bit, that when we think about policies for applications, in addition to incentivizing the adoption of the vehicles, for example, or the other applications, the rest of the supply chain usually requires some formulation of policies as well. So think about encouragement for the adoption of renewable fuels, for example, in those pipelines, and think about the kind of investments that are needed for the infrastructure that come with them. So usually it's a portfolio that covers the application space, the fuel space, and then also the infrastructure space as we think about portfolios.
Thank you, Dave. Another question?
Great. Another question is, can you speak to the safety aspects of the hydrogen economy? Is safety a tractable issue, or are there outstanding issues that need to be addressed?
So, very good question. Anytime that we are dealing with energy, either electric energy or chemical energy like we have with fuels, we must be concerned and very vigilant about safety. The good news is that hydrogen has been handled safely in society for many decades. And we know that hydrogen has different features than other fuels that we use in society. And once you understand those features, we can design the infrastructure to handle hydrogen very safely. As a matter of fact, hydrogen has some interesting features that one might think would make it more hazardous than others, and some other features that would make it more safe than other fuels that we handle in society. So I want to just give an example. It has broad flammability limits that would tend to say, hey, maybe it's more risky than other fuels. But on the fuel lean side, where it matters, it's actually even more safe to leak out than other fuels, interestingly. And it's also lighter weight and diffuses much faster. So in the case of a leak circumstance, it's actually safer than most other fuels that we are handling in society. But we still must remain vigilant, and we know how to actually safely handle hydrogen in society. Anyone else want to make some comments on that? On the panel, you can raise your hand if you'd like to add to that. I teach a whole 1.5-hour lecture on all the hydrogen safety aspects. And so it's actually a complicated set of issues that you must address if you want to handle hydrogen safely in society. So again, it's not an easy answer, but it's an answer that we have technological solutions for today.
Hey, Jack, I can mention
Yes,
on the light duty vehicle side, there are FMVSS, which are the US federal safety standards, crash standards for the vehicles, for fuel cell vehicles that are no different, and we have to pass the same sort of crash test as conventional gasoline or natural gas vehicles, for example. But in addition to that, there's a global technical regulation for fuel cell vehicles that goes above and beyond the US as well as European crash standards to assure that the tanks and all the other fueling components that are unique to hydrogen fuel cell vehicles are safe, are durable, and perform as expected in any sort of serious incident you would potentially have on the road.
And one other reference that I might add to somebody that has questions about safety, the American Institute of Chemical Engineers in the past year has formed the Center for Hydrogen Safety. It's a place where all of the safety information, the testing, the standards, and the protocols have been centralized. So if you have questions about basic hydrogen safety and handling, it's a great place to start that conversation, for example, for more information.
Yeah, terrific organization, and really gathering experts from around the world, and also publicly making all of this information available. Thank you for that, Dave. Center for Hydrogen Safety is what it's called. Okay, well, thank you all for your questions. Very insightful questions, and I appreciate the panelists helping me to answer them too. I'd like to turn things over to the industry panel now, and to expand upon their findings in the roadmap. Our panelists today are Andy Marsh, CEO of Plug Power, Bob Wimmer, Director of Energy and Environmental Research Group at Toyota Motor North America, Wayne Leighty, Hydrogen and Fuel Cell Business Development Manager at Shell, Dave Edwards, Director of Hydrogen Energy at Liquide North America, Mark Monroe, Data Center Advanced Development at Microsoft, Bob Mount, CEO of Power Innovations, and Neva Espinoza, Director of Research and Development, Low Carbon Technologies at the Electric Power Research Institute. So it's now my pleasure to turn this over to Andy Marsh, CEO of Plug Power. Andy?
Well, thank you, Jack, and it's a pleasure to be speaking with everyone here today. And I'm going to tell you a little bit about that. If you go to the next slide, Connor, that hydrogen is here today. So let me tell you a little bit about fuel cells and Plug Power. We've developed the first commercial market for fuel cells. And those fuel cells are used in forklift trucks, which may not be the sexiest market in the world, but you know, the market that's the first that's been developed. And you know, just to tell you how far developed this market is. So as we all sit at home during this COVID crisis and are eating our food from the retail stores, more than 25% of the food that goes to your home have been touched by Plug Power's forklift trucks on the way. And so this business and this industry is essential to the United States and to the world, and it's really kind of being demonstrated during this crisis. So if you take a look at Plug Power over the years, we've shipped over 40,000 fuel cells into this application. But we've done more than the fuel cells. We've built the hydrogen fueling stations to support that activity. We've built 100 stations, and those 100 stations use about 28 tons of hydrogen a day, equivalent to 56,000 gallons of gasoline. Additionally, we've done a lot of fuelings. We've done 28 million fuelings in our life. When you run 500 million hours, you end up doing a lot of fuelings. And we're doing this with people who are household names. Our three biggest customers are Walmart, Home Depot, and Amazon. I think everybody in the audience has heard of them. But the other customers on this list, which we've done a great deal of deployments with, I think you all know also, people like GM, BMW, you know, a impressive list of people who've used fuel cells. And as we've gone about, we take a look at why do they use these products. They use these products because we add value to their operation. More than just sustainability, and all of them have aggressive sustainability goals, especially many of them have been developed over the past year. But by using a Plug Power fuel cell, you know, essentially people can move their goods 10% faster, which equates to a $900,000 saving. And even though the cost of electricity may be slightly lower, fuel cells, because of the value in allowing them to move goods faster and for longer range, as well as the fast fueling aspect, is really what makes it different. And if you go to the next slide, Connor, I think the next slide, Connor, if you think about that, you know, we've built a lot of fueling stations. We've built over 100 fueling stations, as I mentioned. And if you're Walmart, you could actually stop at fueling stations starting in Lewiston, Maine, on the far, far East Coast, all the way to Apple Valley, California, and they could stop at stations that Plug Power has put in place, both inside and outside of those sites. So it's a large, large market opportunity. And as these companies have developed rather aggressive sustainability goals, they've been putting a great deal of pressure on Plug Power to develop green hydrogen. And we've made 2 recent acquisitions, have made other announcements about how we are going to be a major player in the generation of green hydrogen, not just by ourselves, but with partners also. But we acquired United Hydrogen, which is the largest private company that ever built a liquid hydrogen station in the US, in Tennessee. We have great ambitions for them, but as I told you during the Q&A, we want the hydrogen to be green. So we acquired Giner ELX, an expert in electrolyzer technology. So we have the technology to take renewable resources like wind, solar, hydroelectric power, use Plug Power electrolyzers to turn it into green hydrogen, and use our expertise at United Hydrogen to operate that, liquefy the hydrogen and operate the plant. And we have ambitions, as I mentioned, to roll out five liquid hydrogen plants over the next 4 years. We'll receive the renewable energy from people like Brookfield and Apex. Brookfield is a $500 billion asset company. And last week we made an announcement that we cut a deal to be purchasing renewable energy to them to feed our electrolyzers, as well as with Apex, a major developer of wind power in the US. We're not going to do this all by ourselves. As I mentioned, hopefully maybe even some members of the panel will do this with us, but we are going to drive forth and put the green hydrogen economy in place, not in 30 years, but in the next 4 or 5 years. And if you go to the next slide, Connor, I really want to highlight that not only is Plug Power moving into green hydrogen, we're also a technology company. We have vertically integrated over time. We have developed, we are the leading provider of stacks in North America. We are now built, and stacks, I think many in the audience know, are the key components in fuel cells. And those stacks, we make our own MEAs. We're building a gigafactory, which location will be announced in the coming month, where we'll make 7 million MEAs, stamp 7 million bipolar plates, and have the ability to generate 500 megawatts of electrolyzer stack. This is going to be a showcase in this country for the fuel cell industry. And it's going to be used in many, many different applications. And you see across the bottom, we use our ProGen modules, which go into items like drayage trucks, which we've done with Gusan, who's an expert in electric drayage trucks. We have contracts in buses, Class 6 vehicles, and large-scale backup power. What's really interesting is the same fuel cell systems and stacks, which are used in our smaller products like the drayage trucks, are really the building blocks to move into not only Class 8 and large-scale backup power, but also into aircraft. So the world is really expanding for the opportunities for hydrogen. So in summary, if you go to the next slide, Connor, Plug Power, we have some short-term ambitions to make this market real today. We're going by 2024, we've outlined a plan to be $1.2 billion in annual sales. We've grown over 40% this year in the middle of the crisis, and we'll be over $310 million. We'll have operating income of $200 million and adjusted EBITDA of $250 million. And in the long run, Plug's not only interested in being a technology leader, but a leader in green hydrogen. So that's the vision and goal for Plug Power, It was a pleasure to speak with you all today.
Thank you very much, Andy. Next, we have Bob Wimmer, Director of Energy and Environmental Research Group at Toyota Motor North America. Bob?
Well, thank you, Jack. Good afternoon, everyone. As Jack said, I'm Bob Wimmer from Toyota's Sustainability and Regulatory Affairs Group in Washington, D.C. I've been involved with fuel cell and hybrid vehicle technologies for most of my career and appreciate this opportunity to share with you an update on Toyota's fuel cell vehicle progress and activities. I'll begin today with our electric drive vehicle history, targets, and current products, and then move on to our fuel cell vehicle portfolio and finish up with the importance of diversification for the growth of the hydrogen economy. Connor, could you go to the first slide? Oh, I see you have it up. Great. This chart shows an image of how the transition from internal combustion vehicles, the gray area, to different forms of electrification may occur in the coming decades. I want to use it to illustrate Toyota's electrification path towards 2050. It started over 25 years ago when we began developing hybrid, battery, and fuel cell powertrains. Hybrid and battery were first to the market in 1997 with the introduction of the original Prius and RAV4 EV. Hydrogen fuel cell technology was much more challenging. It took us over 15 years and millions of miles of testing before this spacecraft technology was ready for mass market. That effort culminated with the launch of the zero-emission fuel cell Mirai in 2014. Mirai, which means future in Japanese, is a global product for Toyota, available in Europe, Asia, and the US. And finally this year, we introduced, or actually reintroduced, battery electric vehicles to the this time in the Asian market. Looking forward, our electrification goal for 2025 is threefold. Roughly half of our new vehicles will be electrified by 2025. Of those 5.5 million vehicles, approximately 1 million will be zero emission, and that could either be fuel cell or battery EV. We are also aiming to have an electrified version of every model we sell in every market. This will jumpstart us on the path to reaching our 2050 challenge goal of reducing our new vehicle fleet CO2 emissions by at least 90%. This is a global target, so of course it will vary based on region. The portfolio of vehicles will vary based on region. Connor, could you go to the next slide? So here I'll talk a little bit about our product offerings and basically our vehicle portfolio. To satisfy the diverse needs of our 10 million plus customers, Toyota takes a portfolio approach to electrification. Hybrid technology provides a strong foundation with over 15 million sold globally and 15 Toyota and Lexus hybrid models available in the US. For customers that want to plug in, we offer two PHEVs, plug-in hybrid electric vehicles, the all-new RAV4 Prime and the Prius Prime. Since the zero-emission Mirai was introduced in 2014, Toyota has sold or leased over 8,500 globally and 6,500 in the US. The great-looking second-generation Mirai, shown in the lower right, will be available early next year and will be able to travel over 400 miles on a tank of fuel. And like all light-duty fuel cell vehicles, it can be quickly refueled in 3 to 5 minutes at a pump or to what you're used to with gasoline vehicles. Next slide, please. So here I'd like to talk a little bit about the unique scalability benefits of hydrogen and fuel cell technology. So a unique benefit of Toyota's fuel cell technology is its modularity. This allows the basic Mirai power plant, that's the fuel cell stack and associated componentry, to be doubled up for Class 8 trucks and buses, optimized for different medium-duty applications by increasing the size of the battery, or actually reduced in size for industrial and warehouse applications. This product diversity increases power plant volumes, allowing Toyota to scale up our second-generation stack and system manufacturing capacity by an order of magnitude over the first-generation system. Next slide, please. Toyota believes both light and heavy-duty fuel cell vehicles are critical to meeting our climate goals and expanding the hydrogen economy. Toyota is currently developing fuel cell products in 4 heavy-duty categories. The first is Class 8 trucks, where we expect to deliver the first of 10 portal trucks before the end of the year. These zero-emission tractors will haul drayage from the Port of Los Angeles to customers throughout the LA basin. In addition to producing no greenhouse gases in operation, these trucks generate no particulates or NOx emissions, which of course have been shown to damage the health of communities near these truck routes. Just this week, Toyota announced its second Class 8 fuel cell truck project with Hino. We expect to see the first prototype of this collaboration operating by the middle of next year. For the Japanese market, we manufactured 100 Sora fuel cell buses to transport participants at the Tokyo Olympics. After the games, assuming they're held next year, we hope they are, they will join our first generation buses in normal route service. We are also working with Hino on a range of medium-duty truck applications in Japan. Finally, Toyota is exploring various industrial applications, such as forklifts, for our fuel cell technology. Though thanks to Andy and Plug Power's success, the bar is rather high in this category. Thank you very much, Andy. Diversification, the next slide. A common theme in the roadmap that you will hear from other speakers today is diversification, whether that is in the feedstock used to produce the hydrogen or the types of vehicles that consume it. The best way to build volume and drive down cost is diversification. For hydrogen, that is using regionally available feedstocks to produce the fuel. For vehicles, that is both light and heavy-duty products, where light-duty applications will drive fuel cell stack and system volumes, spurring innovation and driving down hardware costs. Medium and heavy-duty applications will accelerate hydrogen demand, improving its availability, as well as driving down its per kilogram cost. This balanced growth of hydrogen supply and demand, along with passenger vehicle-driven fuel cell system improvements, are critical to accelerating the growth of the hydrogen economy. Thank you for your attention, and I look forward to your questions. Back to you, Jack.
Thank you, Bob. And next we have Wayne Leighty. Wayne is Hydrogen Fuel Cell Business Development Manager at Shell. Wayne?
Hi, everyone. It's great to be with you today. Yep, my name's Wayne. I'm Hydrogen Business Development Manager for Shell, responsible for North America. The next slide just asks you to please not make investment decisions based on my comments today. The following slide, you can see at Shell in our new energies business, we are developing the full range of new fuels, and hydrogen is one of those. It means we take a rather objective approach to hydrogen, understanding its relative positioning, advantages, and challenges. And then my job, along with a large team, is to deliver the kind of progress that's needed in hydrogen that begins to open the opportunities that we're talking about today in a roadmap. On the next slide, you can see our hydrogen business is already growing quite rapidly and globally in the first steps, the early steps of that roadmap, largely relating to mobility, hydrogen as a fuel. We're a member of a joint venture in Germany called H2 Mobility that's progressing toward as many as 400 hydrogen refueling stations. In the US, on the West Coast in California, we have 9 operating now and are nearing completion of 3 refueling stations serving the same drayage trucks that Bob spoke about for the ports of Los Angeles and Long Beach. And then we've just begun a program to develop 48 more hydrogen refueling stations in California. Other things to note, I identified in Japan, part of a consortium that's now in sea trials of the first liquid hydrogen ship. and several electrolysis projects in construction and announced in planning. On the next slide, you can see we're delivering this through a tremendous pace of progress. It's really encouraging across new energies and in hydrogen to see costs coming down so fast as performance and scale increases so fast. Our next hydrogen refueling station is double the performance at half the cost of the ones that we are just finishing building now. On the next slide, you can see the same image of hydrogen drayage trucks and the refueling stations that are in commissioning, about to open for the ports of LA and Long Beach. On the next slide is the 10 megawatt electrolyzer that's in construction at a refinery in Germany. On the next slide, there we go. And my last slide is announced plans at the gigawatt scale, so offshore wind from the Netherlands and the firming of that intermittent power production through large-scale electrolyzers. Thank you very much. I'll keep it short and look forward to your questions.
Thank you very much, Wayne. Next, we have Dave Edwards. Dave is Director of Hydrogen Energy at Air Liquide North America. Dave?
Thank you very much, Jack. It's certainly good to go a little bit later in the presentations because I can build off of the previous, but let's go to the next slide. So just to start off with, Air Liquide is a company that is supplying hydrogen into these markets, and we've been supplying into these markets for quite some time, but it's just part of our portfolio, and the same with many of the other companies on this call today. Hydrogen is core to our technologies, but it builds on the other things that we've been doing in more than 100 years of existence for Air Liquide. So go to the next slide, please. If I focus on the hydrogen side of the business, I think as Jack pointed out at the beginning, hydrogen is not new to the world of industrial gases. We've been using it in our company for more than 50 years as a product, both production, supply chain, distribution, as a global basis. We have pipelines, we have liquefiers, all of the mechanisms to distribute hydrogen and produce hydrogen are things that we're active in today, focused very much around things like oil and gas industries, electronics industries, steel and glass applications, and traditional transportation applications like space, for example. And just for some of the key figures to reference what we're doing today compared to what the roadmap is calling for, we already produce more than 14 billion cubic meters per year. We have thousands of miles of pipelines and hundreds of production facilities globally focused on this industrial side of hydrogen. But that's not the future that the roadmap is talking about. Let's go to the next slide. The roadmap really ties in the US direction with the global view of where hydrogen could be going. And I'd like to reference the Hydrogen Council, who formed a few years ago in order to provide this global view of hydrogen as it can develop into the economics globally. We now have more than 92 members, and I'll call back to some of the roadmaps that they've put together on a global basis to look at where the US fits in with that for reference. We go to the next slide. I'm going to focus now on, the roadmap has some grandiose plans, has some aspirational plans, and people question, is this real? Can we really do the kind of things that are in here? Well, as a society, we've challenged ourselves with very difficult milestones. And what I'd like to show is that the things we're doing today are already building on that roadmap and enabling this roadmap to come to life. And so let's look at some of the things that just Air Liquide is doing from an investment perspective in the Americas. Go to the next slide, please. So two projects that I'd like to point out. The first one is a production facility in Nevada. It's the first time that Air Liquide has put large-scale production facility into a market dedicated specifically to these new energy markets, not dedicated to our traditional industrial markets. It's a $150 million investment. It has 30 tons per day of production, including liquefaction. And it's located in the West Coast, near to where our California markets are and where many of the markets that Andy pointed out earlier for warehousing, for example, exist. Construction began earlier this year, and we expect operation about a little bit more than a year from now, to have operation of that liquid supplied into those markets. The second project I'd like to talk about is in Quebec, and that's, for us, the world's largest PEM electrolyzer project with 100% hydrogen produced from renewable electricity. It's a $40 million investment for us, producing 8 tons per day of liquid at an existing location where we do some industrial work in Bécancour, Quebec. The construction began last year, and we expect operations and delivery by the end of this year. If we go to the next slide, it's always nice to talk about roadmaps, but until you actually can walk up and touch something, you may not believe it. I can't bring you to the site because of our travel restrictions, but I'll bring you some pictures of what's happening in the desert in Nevada, for example. And what you see are site prep and foundations being poured. And most importantly, we start to build our storage facility. That item at the bottom that looks like a Martian invasion, perhaps, is actually the sphere for storing the liquid hydrogen from the liquefier in our production facility. And these pictures are just, some of these are as early as this week, or as recent as this week, to show that this is real progress being made, real dollars being put into the ground. And if I go to the next slide, we can show some of the same things at Bécancour. An electrolyzer project isn't quite as big and grandiose. It tends to be smaller modular systems, but you can see the electrolyzers and the electrical infrastructure being built by our team in Bécancour. So real projects really hitting the ground and showing that this roadmap is real and can be achieved. We go to the next slide. And a comment about electrolyzers is that the scale-up has already started. Electrolyzers aren't a vision of the future. They're a technology of today. We've already seen more than 30 electrolyzers in operation that are in the scale of 50 to 100 normal meters cubed of hydrogen. We've seen investments like the project that Liquide is doing that we talked about under construction, and scale up to more than 100 megawatts heading to the next phases. So this is an active technology that is ready for scale up today. Go to the next slide. And some of the other investments. Investments aren't always hardware in the ground. Sometimes it's finding the right partners for the market. Sometimes it's the right kind of technologies that we want to invest in, and a variety of different announcements that we've made just as Air Liquide. And if you think about every other company that's on this panel and every other company that participated in the study and every other company that's in the hydrogen market, they could put up some similar slides showing these kind of investments. If we go to the next slide. So with that, I'd like to conclude, and as the panelist who represents hydrogen production, look forward to any of your questions about hydrogen and its sourcing. Thank you.
Thank you very much, Dave. Next, we have Mark Monroe. Mark is in the Data Center Advanced Development at Microsoft. Mark?
Thanks, Jack. And apologize for the change in my appearance from the picture that was on the first slide. We got to get an update on that, eh, Connor? So let's go to the next slide. I just want to start off, since I'm the only person here who's from an end user of hydrogen company, not somebody that makes hydrogen or makes fuel cells or integrates those into systems. And by the way, we've worked with many of these companies and are looking forward to the continued future. I wanted to give you a little bit of background in case you're not familiar with the term hyperscale. And we'll talk about, I want to talk about that in terms of the speed and the size with which the industry that I work in is moving forward. You'll sometimes hear these companies referred to as digital infrastructure companies, and there's about 24 companies in the world, the names are probably familiar to you, Microsoft among them, that are considered hyperscale companies. And so let's talk a little bit about speed and size. This is a picture of our CEO, Satya Nadella, talking at a conference in November last year. And he's talking about the amount of storage that's going to be required on the internet and the timing of that. So let's go to the next slide, Connor. Satya said, we're going to move to about 175 zettabytes of data by 2025, 5 years from now, up from 40 zettabytes today. And if you don't know what a zettabyte is, there's a little guide for you on the right-hand side of the slide. A zettabyte is 1 million petabytes, 1 billion terabytes, or 1 trillion gigabytes, okay? So we need 135 trillion gigabytes more storage just in the next 5 years. That device that's pictured there next to the list of terms is a product that will store about 1 petabyte of information. It'll store 1 million gigabytes of information in a space of about 22 square feet. Each of those cabinets takes about 17 kilowatts of power. And so if we think about the 135 million of those devices that we'll need in the next 5 years. It'll take up 105 square miles of space and require about 2.3 gigawatts of electricity. So let's go to the next slide. I've laid that out for you in Los Angeles. That would be a square that goes from Long Beach to north of Compton and from Torrance all the way over to Lakewood. So, you know, if you live in that area or you know people that live in that area, tell them to get out of the way because we're going to need that. Plus, if you go to the next slide, Connor, I think the two nuclear power plants that'll be required for the amount of power that goes into that. So that gives you an idea of scale. One more of scale that I'll give you if we go to the next slide. This is a town of Boynton, Virginia, in the eastern part of the US where Microsoft has one of our data centers. The light yellow lines where the arrow is pointing is the town of Boynton. The darker yellow lines are the land that Microsoft has purchased, and you can already see the beginning of the data centers that are there. This picture is about 1.5 years old. And all of that kind of long strip space where there are buildings is now filled with data centers. And plans are that we'll end up filling up the rest of this within the next 5 to 10 years. 2 more slides on scale. Let's go to the next slide. This is a picture of our facility in Quincy, Washington, which is in the eastern part of Washington State. The buildings in the background, each one of those squares represents about 8 megawatts of capacity. And if we go to the next, which you can look at from the current satellite, there's the yellow arrows are pointing to the buildings that we were looking at in the last slide. And you can see that there are now 4 more buildings and a 5th one under construction. And the 4 additional buildings are much higher capacity. They will consume more energy than the existing ones that are there on the site. So hyperscale is all about size, it's about speed. And at sites like this, when we start thinking about backup power, we have a difficult problem. Let's go to the next slide. And this is how we get into the hydrogen story. Every data center company in the world, whether it's one of the 24 hyperscale companies or one of the tens of thousands of companies that have data centers around the world, has a problem with power. We need continuous, reliable power, and today the way we do that is we provide backup power with diesel generators. Every company that I'm aware of uses diesel generators. The problem with these is that they're noisy, they pollute when they run. The air quality permits are difficult to get. They take long times, and at the scale that we're talking about, if you think about the number of buildings that we have on that Quincy site, we run into difficulties getting the air quality permits at all. We've also come into some discussions with folks like the California Energy Commission, which recently put some guidance out about data centers in California needing to be able to run for 96 hours, potentially 96 hours without grid power because of climate change and the changes that are going on there. And they've in the same breath told us that we cannot use diesel to run for 96 hours. And so we're left with what kind of high energy, long duration storage solutions can we use to provide that backup power? And that's why we're working with hydrogen. If we go to the next slide, this is a concept of what our 3 megawatt diesel generators look like at many of our data center sites. The diesel is inside of an enclosure, and you can see a person-sized door there that gives you an idea, a sense of scale. And on the right-hand side is a concept of what might look like to have a hydrogen fuel cell powered generator there. It takes up a little bit more footprint depending on how we do the storage, whether we use liquid or gaseous or even a pipeline perhaps as a backup source. And whether we combine those tanks into a larger scale that might look something like the next slide. Because at one of those sites, let's go to the next slide, Connor. At one of those sites where we have maybe 30 megawatts of power, it'll require something on the order of 100 tons of hydrogen to be stored on site and sitting waiting to be used for backup power. So that'd be a 60-foot sphere of hydrogen for each 30 megawatt building that we have on one of those sites. And again, Microsoft's not the only player in this game. there are the other 20 companies that are all in the same kind of a boat looking for pollution-free backup solutions. Now, if we have that much hydrogen sitting around, we don't believe that it should just sit. Today, we're prohibited from running our diesel generators to participate in things like curtailment of energy off the grid or providing energy during peak use periods. But if we go to the next slide, we see the ability to put pollution-free generators in the data center as an entry into a larger hydrogen economy. We think that we can participate in utilities to provide ancillary services to the grid, that we can help to firm up the variable generation characteristics of renewable energy and solar and wind. Pairing fuel cells with electrolyzers on site could let us to store curtailed energy for use later to take data centers offline essentially, or it could be shared with vehicle fueling applications or material handling applications like Andy talked about, and potentially even putting it into natural gas lines to decarbonize natural gas and participate in the economy that way. So we naturally view the data center as the center of that hydrogen economy, but we're very positive on the move forward. And we see the U.S. hydrogen report as just the beginning of that roadmap moving forward. So I'll turn it back to you, Jack.
Thank you very much, Mark. Next, we have Bob Mount, CEO of Power Innovations. Bob?
Let me try and adjust this camera and see if we can get some better lighting here. Appreciate being here, and I appreciate being able to work with a lot of the people that are on this panel. Power Innovations is a 23-year young company, and we basically started 23 years ago with power independence and power quality. We were focused and still are on critical, rugged, and custom solutions. About 8 years ago, we really, in our renewable line, got extremely focused. We were involved in a partnership with Daimler and Mercedes-Benz, Hewlett-Packard Enterprises, and the Department of Energy and their NREL lab, renewable labs. And the intent was utilizing hydrogen in that data center arena to be modular, to be scalable, and that began the project. And one of the advantages of the hydrogen was to be able to take that hydrogen fuel cell system and run it within the data center and not solely on the outside of the data center. What I wanted to do on this slide right here that's up is, show what does a hydrogen economy look like. We saw in the roadmap some sections of this, but as you can see, it can address all of the current commercial and quality of living needs in a quite green and exciting way. So what we would like to do is show some of these applications as we've done in some of these other presentations that are here today. So if we go to the next slide, great. What we were wanting to do is utilize these fuel cell systems to do a sample backup test within the data center. And working with Microsoft, we took a 1/4 megawatt load and we ran that at full load for a 48-hour period. And a lot of fun things happened, but as you can see down below, in that time frame, we produced 10,560 kilowatts of power. We produced 7,000 liters of pure water and consumed 814 kilograms of hydrogen. So yes, it can be done. If we go to the next slide, here's something that's happening as we speak today. There is an event called the Rebel Rally. And basically what it is, it's a course that goes through Nevada and California across the deserts, and it tests navigational skills. You're not allowed to use GPS system, and it's an all-woman event. And a lot of media will be focused on this, but they came to us and said, can you power this event totally green? And what is unique about this event this year is they're going to be using battery electric vehicles. And over the period of the event, we are going to be delivering 4,000 kilowatt hours of power for the vehicles, and daily about 53 kilowatts of base camp power, per 153 per day. And that right there we call the MEC, but that's one of the vehicles there that will be supplying that power. So very exciting over the next 10 days to see how that comes to play. So if we go to the next slide. You're probably all familiar with towable generators. This one right here that you see will be a hydrogen system. And you can see with the options there, low noise, zero emissions, easy to transport, scalable, fast refueling. A lot of more information will be coming in the next couple of weeks about this system, with a couple more exciting capabilities that it will offer. On your next slide. Now we're scaling up here. If you look at the picture, the above picture, that is what we call our hydrogen battery electric vehicle DC fast charge systems utilizing hydrogen. So it will store hydrogen and also the fuel cell systems to do DC fast charging. The actual charge pumps that we're looking at here will have capabilities of over 190 kilowatt hours. The intent here is to be able to put these units in areas where utility is too costly or not available, but it allows now, with the use of hydrogen, to address a battery electric market anywhere, anytime. And then down below, you'll see here, this is our scalable systems, as was indicated here. These are 1.5 megawatt modules that basically allow primary or backup power to a larger scale, whether that be for a data center application or a commercial business application, but it shows you the scalability. If we go to the next slide, we get more excited here when we get into communities, and basically when we're able to power communities in the form of gardens, utilizing hydrogen technology and also electrolyzing and reforming, with the byproducts, not only the power, but also the ability to maintain these gardens, and with carbon capture and other advancements, be able to use all of the aspects of the fuel cells for a green and exciting world. So hopefully that's been a little bit of an eye-opener on some of the things that are happening. Again, appreciate being here and working with a lot of the people that have presented. So back to you, Jack.
Thank you very much, Bob. And finally, we have Neva Espinoza.
Here is to be able to put these units in areas where utility is too costly or not available, but it allows now, with the use of hydrogen, to address a battery electric market anywhere, anytime. And then down below, you'll see here, this is our scalable systems, as was indicated here. These are 1.5 megawatt modules that basically allow primary or backup power to a larger scale, whether that be for a data center application or a commercial business application, but it shows you the scalability. If we go to the next slide, we get more excited here when we get into communities, and basically when we're able to power communities in the form of gardens, utilizing hydrogen technology and also electrolyzing and reforming, with the byproducts, not only the power, but also the ability to maintain these gardens, and with carbon capture and other advancements, be able to use all of the aspects of the fuel cells for a green and exciting world. So hopefully that's been a little bit of an eye-opener on some of the things that are happening. Again, appreciate being here and working with a lot of the people that have presented. So back to you, Jack.
Thank you very much, Bob. And finally, we have Neva Espinoza, Director of Research and Development for Low Carbon Technologies at the Electric Power Research Institute. Neva?
Fantastic. Thank you, Jack, and thank you so much for inviting me to be here today. I'd also like to thank all the other presenters. Great insights, exciting technologies, great progress that's being made in this space, and a pretty impressive group of innovators to help us transform our energy system moving forward. So, as Jack mentioned, I'm from the Electric Power Research Institute. For those who may not know us, the Electric Power Research Institute, EPRI, is a nonprofit R&D organization that looks at the end-to-end energy system, right? So from power generation, transmission, distribution, and end-use activities, and all of the technical challenges around that arena. So we've heard a lot today. We've heard about the U.S. roadmap. We've heard around specific technologies and low carbon resources, strategic directions of companies, and how they are addressing some of those technical challenges moving forward. So I thought what I would talk about as kind of the closeout of the presentation session is about why are we doing this? Why is it important? And why is it important right now? Because we have been hearing about hydrogen up and down for years, on and off like a roller coaster. So let's start with the idea of we are seeing across organizations, governments, companies, regions of the world, significant carbon reduction commitments being made to improve air quality, being made to address climate concerns around the world. Climate change is a global challenge, but we need to be making significant improvements in this challenge in progressive countries to help lead the way in demonstrating practical and scalable solutions that will enable deep decarbonization. In Denmark, we see significant investment in wind. In Germany, we see significant investment and commitment to solar. United Kingdom has put significant leadership out there in terms of carbon reductions. And all of these different countries around the world provide significant lessons learned for us. In the US, we're starting to see more and more companies make commitments to reduce their CO2 emissions all the way to the point of net zero CO2 by 2050. So let's talk about just a little bit what are global CO2 emissions, how does the US fit in that picture, and what are the things that we are doing as a country that will enable this deep decarbonization across the economy. So if you were to go look at a graph of global CO2 emissions on an annual basis, you would see something that looks like this. It's just continuing to go up. Matter of fact, if you go back to 2005, you'll see global CO2 emissions have risen quite significantly. But in that time frame, there have been 36 nations who have actually reduced their overall CO2 emissions. Of that entire net reduction, the US has accounted for 44% of those global reductions, and the electric sector within the US has accounted for 80% of that 44%. So have made significant contributions to overall CO2 reductions in our country. Now, if you look at this from an economy-wide scale, let's go back to 2005. In 2005, US CO2 emissions were about 6 gigatons of CO2. The electric sector made up 40% of that. Now let's fast forward 15 years to today. Today, we see the US CO2 emissions being about 5 gigatons of CO2. So we essentially have 1 less gigaton, 20% less CO2 emissions than we had 15 years ago. We've done this while maintaining electricity price relatively constant year over year on an inflation basis. And we've done it with a growing economy, about 28% in that time frame. There's 2 core things that have got us there. One is strides we've made in energy efficiency. And when I talk about that, I mean total primary energy over our gross domestic product. And the second is cleaner electricity generation. So much that the US generation fleet is approximately 30% less carbon intense today than it was in 2005. Now let's fast forward another 10 years and say, okay, we want to continue to reduce our overall CO2 emissions in the US. What will it take? And at EPRI, we see 3 core things being part of that. One is continued strides in energy efficiency that will always be part of this conversation. The second is continuing to lower the carbon intensity of our US generation fleet. approximately 50% cleaner than it was in 2005. And the third thing is something you've heard others talk about today a little bit, is around efficient electrification, essentially using a cleaner electric grid to enable and power other parts of the economy that are more carbon intense. We see projections of having about 20% of vehicle miles traveled electrified miles by 2030 being a very realistic, not easy, but realistic goal for us to achieve by 2030. When we look out beyond 2030 and we look out to 2050, we're looking at what is it going to take to get greater than 80% carbon reduction across the entire economy. So even though we're going to continue to make strides in energy efficiency, and even though we will continue to focus on a cleaner electricity fleet, so much that that fleet may essentially be low to no carbon by 2050. And even though we're going to continue to electrify all the pieces of the economy, we can reasonably do that. Those three pathways alone will not be enough to enable an economy-wide decarbonization greater than 80%. We need other tools, we need other options. And that brings us to the idea of low carbon resources, exactly what we're talking about today. Hydrogen, ammonia, synthetic fuels, and biofuels are going to become such an important part of our energy system moving forward when we are trying to achieve deep decarbonization across the economy. More than 40% of the economy today is not well suited for direct electrification and is very carbon intense and does not today have a scalable, affordable way to transition to be a low carbon part of the economy. And this is exactly why EPRI has been working with GTI, the Gas Technology Institute, another nonprofit R&D organization who has historically looked at the gas sector, to come together and launch something we call our Low Carbon Resources Initiative. As part of this initiative, our two companies are coming together, and we have 21 other companies who have joined us to date, to really look at this overall low carbon resource economy and what is it going to take. I talked about the importance of these four pathways, four options, right? We need something else other than energy efficiency, cleaner electricity, and efficient electrification. So I just want to harp on this optionality idea for a minute. Optionality via hydrogen, ammonia, synthetic fuels, and biofuels brings so much to our energy system. One is optionality drives resiliency across our energy systems. As we shift to, you can go back to my first slide, it's okay. I'm abandoning my slides and just talking, no problem. Optionality drives lots of different, drives resiliency across our low carbon resource system. So when we look at our entire energy system, we need to not just make sure that we are clean and we are reliable and we are affordable, but we also have to be resilient and have backup options. As one option goes away, we need others. The other thing optionality drives is competitiveness in the market, which drives down costs and drives up affordability over time. So all very important pieces of our system. If you'd like, you can go to slide 2. So I would like to show here some of the leadership we have seen through the Low Carbon Resources Initiative. We're working closely with 21 companies across the spectrum of low carbon resources, and we very much welcome you to learn more and engage with us. We've also created opportunities to engage with the global R&D community. So when I say that, I mean the importance of working with national labs, the importance of working with universities, the importance of working with global subject matter experts in this space to accelerate and enable technology development and commercialization in the next 10 to 15 years to ensure we have technology options that are scalable and affordable by 2050. So with that, I would just say our goals are aggressive. Our timeline to achieve them is quite short, and the technologies available today still have some headway to move forward in terms of that scalability and affordability. We've talked a lot on this panel about how hydrogen is available today and we use it. We very much do use hydrogen today. Hydrogen is an energy carrier that is used across the economy, but it is a high carbon energy carrier because it is created from mostly carbon intensive sources. We need to identify ways and enable ways to affordably make it a low carbon energy carrier through various carbon mitigation and management strategies. So with that, you can jump ahead to our last slide here. Please, I'm looking forward to the conversation. I'm being mindful of time. One more slide. And please take a look at our website, check out some of the really exciting work that's going on. Thanks so much, Jack. Back to you.
Thank you all. So fantastic presentations from all of you. Appreciate it very much. At this time, we will like to hold our second Q&A session. And I ask that you all put your cameras back on, please. And as a reminder, should you have any questions, please submit them through the questions box on GoToWebinar. So Connor, do we have any questions?
Yes, one question to kick things off. What is the status of hydrogen development on the East Coast?
Well, I guess I can take a shot at that, then maybe pass along to Dave. As you know, Air Liquide and Toyota are working together to launch light-duty fuel cell vehicles and stations in the Northeast. We are moving forward with that process. The stations are coming online, and the vehicles, once there are a sufficient number of stations, Toyota and other auto manufacturers will be bringing vehicles into the marketplace in the Northeast. So it's moving forward, and I'll pass along to Dave to give you a little more information on the remainder.
So first Dave and then Andy.
Yes, thanks, Bob. So yeah, Bob's talking about the light duty vehicle station network and station introduction in the northeastern states of the U.S. And he's exactly right that we have a number of stations that are ready to go and a number of other stations in development. So we're looking forward to that market expanding. But the Northeast is a lot more than just light duty vehicles. It has the same energy challenges as other parts of the country, and some unique aspects in the Northeast. And so if you recall back to my presentation, I showed some investment in Quebec, for example, to bring liquid hydrogen, renewable liquid hydrogen into those markets. And that's actually intended for the Northeast United States, not just for the light duty vehicle applications, but think about the medium and heavy duty applications, the data centers and the warehouses that Andy probably wants to talk about here in a second.
Yes, Andy.
I think you hit it on the head, Dave. I was going to say, boy, if you shopped at Walmart or you had home delivery from Amazon, you probably had a product that was touched by a fuel cell over the last 9 months. And if you take a look, we do a lot of work, and it's even green hydrogen in many cases. We do a lot of work with Leighty out of their Niagara plant, where we probably source 10 tons of hydrogen in the Northeast from Leighty, from that plant. As well, I think a little from you in Canada, Dave, and other people on the panel. So hydrogen is in the Northeast in forklift trucks and soon in other applications, as Bob highlighted.
Thank you. Next question, Connor.
Yep, I think we have a question that's directed towards Neva. Can hydrogen blending and natural gas infrastructure be coordinated with asynchronous renewable power generation to provide an incremental approach to a hydrogen economy? Is there a roadmap to coordinate the renewable power, gas utilities, electric utilities, and hydrogen industries for this approach?
Great, that's a fantastic question. So yes is a short answer. So there's a lot of people looking at a lot of different innovative energy systems. So for example, I think earlier in the panel, we talked a little bit about how do you manage intermittent power? How do you manage the need for additional flexibility on our power systems? You see our nuclear units, you see some of our gas units, our renewable units having very different demands in different regions of the country. So can you potentially use that off cycle, if you will, electricity, produce, hydrogen with it via electrolytic hydrogen via electrolysis process, take that hydrogen and blend it into natural gas pipeline. So there's a lot of challenges, of course, around that blending. There's been a lot of work done in different places around the world. Recent studies in Europe, specifically in the UK at Keele University, has looked at blending up to 10-20% in different pipelines. And you see different impacts on end use of applications. Most studies out there will tell you you can blend 10 to 20% without really having significant impact on end use applications. It is important to note though, with that blending, even if you have a 20% blend of hydrogen, which is typically by volume when people say it in the pipeline, you're not going to get a linear decrease in CO2 emissions. A lot of times those are nonlinear relationships. So what sounds really easy and typical has a lot of complexity when you get into the science behind it. But a lot of great research going on out there. The national labs have put a lot of work here in the US and looking at blending of those pipelines. The Gas Technology Institute that we've worked on has a lot of history in that space too. So I think you're going to see more and more of these integrated energy system types of projects and demonstrations as we move forward.
And it's important to realize the magnitude of the contribution that can be made by this idea, though, because the transmission and distribution of all that renewable energy via the gas system and the magnitude of storage that it implies would be a huge benefit to making more renewables on the electric grid. So this is a very important idea for doing, for moving towards a green hydrogen economy. Very important idea to mix it into the gas system.
I would agree with that, Jack. And I would add too that hydrogen, its chemical energy storage capability has a ability to move electricity or anything through space and time. Yeah. And that weekly, monthly, seasonal storage capability that this potentially brings into our integrated system changes the way we look at energy moving forward.
Absolutely, and it's required for us to reach our zero emissions policy goals. Okay, another question, Connor?
Yes, one that I think applies to most of the panelists here. Can the panel speak generally to the common presumption of why not just use batteries or why not just use electricity?
So batteries have a very important function and are not directly competitive with hydrogen. Hydrogen offers different features than batteries do. So for example, in transportation applications, if you need rapid fueling, long range, or heavy payload, hydrogen has advantages over batteries. But if you have a short duration, you don't mind charging for a long time, then batteries are more efficient. Okay, so they're not competing. They have complementary characteristics. In addition, for example, if you want seasonal duration of storage, batteries suffer from self-discharge, but hydrogen doesn't. If you need a massive amount of energy storage, but small power, hydrogen and fuel cells can scale independently in power and energy, but batteries can't. So you can see that there are complementary ways in which batteries are better for short duration and for applications that don't mind the weight, for example, in transportation. Hydrogen is better for rapid fueling, long range, seasonal storage, and things like this. So that I suggest they're complementary zero emissions solutions. Anyone else on the panel want to add to that?
I do.
Yes, Neva.
A diverse set of many solutions is going to be the pathway to enable deep decarbonization. We can't do it with one thing. We can't do it alone with energy efficiency. We can't do it alone with clean electricity. We can't do it alone with electrification, and we can't do it alone with low carbon resources. So it's going to be required to have all of the above, and it's going to be required for resiliency of our energy systems.
And Andy?
Jack, I always look at customers, and I have this chart that DHL shared with me, and this is about transportation. And it shows because of the weight and energy density of batteries, they can, a usable truck could go about, this is a class 3 truck, could go about 125 kilometers. I think you heard this presentation, Jack.
Yes,
and
I
Akam
did.
said after 125 kilometers, I'm going to be pulling batteries, not delivering packages. And to me, that's really kind of the key. And with fuel cell solutions, because of the energy density and weight advantages, you can go about 5 times further for their use case. So I think it really highlights the fact, there's certain apps where, driving to work for me, a BEV is perfect. Driving 300 miles, and then back, maybe not so with packages.
Yes. Another question, Connor?
Great. Another one. Do we have enough wind or solar resources available for now or for the projected future to give us the capacity for hydrogen to supply 14% of our energy supply in 2050?
So not only do we have enough for 14%, we have enough and it's diversely available all around the world, much more diverse than the fossil fuels that we use for most of our energy conversion today. So absolutely, we have plenty of sun, wind available, and it's available all around the world. So this is it's a wonderful transition to make it more ubiquitous than current energy sources are. Next question.
Great. Another question is storage in the terms of methanol storage. What is the progress on that?
Anyone in the panel want to get that one? Yes, Dave.
So I'll answer a more general question about hydrogen carriers broadly. Methanol is one way that you might think, instead of just moving hydrogen from point A to point B, you might think about moving it in other, either chemically bound or other mechanisms. You can liquefy the hydrogen, you can gasify the hydrogen, or you can carry it as methanol, you can carry it as ammonia, and there's other various organic carriers. And there's various levels of development. Things like ammonia and methanol, known chemicals, known conversion processes with economics that are scalable and known, give us some boundaries of places to start. But some of the carriers that are in development might also provide interesting options for the future. So I'm not directly answering the question about what's the status of methanol development for transportation, but it is one of many options available and will be part of the mix for the energy future for those places that do have difficulty producing hydrogen locally.
Yes, and many different options, even liquefying it, moving it at high pressure, moving it as a chemical that's a liquid at room temperature, at atmospheric pressure and temperature conditions, and these kinds of things are very important vectors for moving hydrogen around in society, and they will be selected based upon the end use requirements, right? If you need a very high energy density and you need to go a very, very long distance, sometimes liquefied is important. If you don't have all those requirements, just compressing it might be sufficient. If you need to go really far and have a huge payload, like a ship, maybe you need methanol or ammonia. All right, I think that we have to end it here unless you have one last question, Connor.
Yes, I think one last one that I think would be good to end things on is, how does the United States compare with the hydrogen economy to other countries or regions like Europe, China, or Japan?
Well, the United States is quite diverse because we have different jurisdictions in all of our 50 states. I want to suggest that most of the states in the Northeast and in California, Oregon, Washington, and these states, we have policies that are very similar to those in Japan and in Europe, and are adopting, as a result, a lot of sun and wind power and zero emissions goals that are set for 2045, 2040, 2050 timeframe to get to zero emissions of greenhouse gas and criteria